All right, in lesson 11.1, we are looking at a new type of hypothesis test called the chi-square test for goodness of fit. This allows us to determine whether a categorical variable with several categories fits a specified distribution. And typically we express that distribution as proportions. So there are a couple of ways we can write our hypothesis. We can write it as sentences saying the actual population proportions are equal to the hypothesized proportions. And then our alternative would be that the actual population proportions are different from the hypothesized proportions. We can also write it in symbols. And if we want to write it in symbols, we would say proportion 1 equals and express that as a decimal, proportion 2 equals, and so on, identifying the proportion that we believe would belong to each category. And then our alternative would be that at least one of those proportions is different from what we expect. Our test statistic then is the chi-squared statistic, which looks like this. Remember, what we do is we take the observed value in each category, we subtract the expected value from it to find out how far off we are from what we expect to get. We square that, so we're dealing only with positive differences, and then we divide that by the expected value to figure out as a percent how far off we are from what we thought the count would be. And then we add all of those together, and that's called the chi-square test statistic. Now, remember, we are looking at the number of categories. We use K to represent that. And so our degrees of freedom is always going to be K minus 1, number of categories minus 1. And our p-value is always going to be represented by the tail of the graph. And the chi-square distribution is skewed. The conditions that we need to check for a chi-squared test for goodness of fit. First of all, we have to have our data coming from a random sample or some sort of randomized experiment. Our second condition is what we call the large sample size condition. And for this to be satisfied, we need all of our expected counts to be at least 5. And then we have the independent condition, which is the 10% condition that we've used in previous chapters. So the only condition that is different with the chi-square test is the large sample size condition. And notice that we are no longer checking the normal condition because the chi-square distribution is not approximately normal. It's a skewed distribution. We're going to do one more example today, and this one is an example where we have maybe some city officials that want to examine traffic tickets given in their city. And what they want to know is, do the proportion of traffic tickets given to drivers of various races mirror the racial breakdown of the city's population? So anyway, the data that we're given is the number of tickets that were given to white drivers, black drivers, Hispanic drivers, and other. And it says that these numbers were obtained from a random sample. Now, the proportion of the drivers in the city broken down by race is given in the second table. So you'll see that 55% of the city's population is white, 30% is black, and so on. And so what we're going to do is carry out a test to determine if the racial distribution of traffic tickets issued by the city is significantly different from the distribution of the population. Now, one of the important pieces of information we need to know is how many total tickets were given. So we would start by adding up the 66, 55, 18, and 9, and that gives us a total of 148 tickets given. And that's important because we'll use that when we calculate our expected values. Now, with the chi-squared test, we're going to go through all of the steps in Phantom, except we don't start by stating our parameter. So we just jump right to our hypotheses. So our null hypothesis is that the racial distribution of traffic tickets issued would be the same as the racial distribution of the city's population. Our alternative is that the distribution would be different. Now, if we wanted to write this in symbols, we would write it like this. So P sub W represents the proportion of traffic tickets given to white drivers. PB is the proportion for black drivers. PH is the proportion for Hispanic drivers. And PO is the proportion for other. And notice that those add up to 100%. Now, our alternative is that at least one of these proportions is incorrect. And remember, we mentioned how it's fine if a couple of them are what you expect, like perhaps proportion for white could be 55%. But if the proportion for black drivers was, let's say, 40%, that would be different than what we expect. And so as long as one of those proportions is wrong, that would support the alternative hypothesis. The next step is our assumptions. We are told in the problem that the traffic tickets were obtained from a random sample, so that condition is satisfied. We're going to calculate the expected counts. And with the Fruit Loops example, we were looking at what's called a uniform distribution, where all of the categories were evenly distributed. So we had like 1/6, 1/6, 1/6. Here, we're not expecting that. We're expecting that most of the traffic tickets would be issued to white residents because most of the city is white. So our expected count here would be 0.55 times 148 or 81.4. And that's because we expect that 55% of the tickets would go to white drivers. There were 148 tickets issued, so we expect 81.4 traffic tickets issued to white drivers. Now we'd repeat that for the other categories. So we expect 30% of the tickets to go to black drivers. That would be 44.4 tickets. 8% of tickets to go to Hispanic drivers. That would be 11.84 tickets. And 7% to go to other, which would be 10.36. And if we add those expected counts together, they do add up to 148. I think they're maybe sometimes can be a little bit off because of rounding, but I think in this case it works out okay. And we want to keep those decimals. Even though we know we can't issue 81.4 traffic tickets, we still keep those decimals in the expected count. Now, for the independent condition to be met, we would have to assume that there are at least 1,480 traffic tickets issued in the city. And it says that it's a large city, so that's probably a safe assumption to make. So we would assume that our observations are independent. Now, the name of the test, again, is the chi-squared test for goodness of fit. And we're going to calculate our test statistic. So we have a table to help you keep things organized. I showed you on Wednesday how you can put these numbers into the list in your calculator, but we'll fill them all in the table just so you remember what calculations we did. So first, I'm going to fill in the observed counts. Those are the number of traffic tickets that were actually issued. We calculated the expected counts when we did the assumption step, so we'll fill those in. And then we need to calculate the 4 separate components of our test statistic. So observed minus expected, square that difference, and then divide it by the expected count. And I went out to 4 decimal places this time because that's what my calculator did. As long as you go to probably 3 decimal places, you're probably safe. You probably don't need to go to 4. But then our test statistic, the chi-squared statistic, which remember we said looks like an x squared, is the sum of those 4 different calculations. So when I add those together, I get 8.828. Now, the category that contributed most to the chi-squared test statistic is Hispanic, because notice, and let's make a note here that our degrees of freedom will be 3, because we have 4 different categories, so 4 minus 1 gives us degrees of freedom 3. Now, again, back to the question, the category that contributed the most to the chi-squared test statistic is Hispanic. That had the largest number of the 4 parts there. 3.2 is bigger than any of the others. And that is because the observed count was farthest away in terms of percentage from what we expected it to be. Now we need to get our p-value. And the first thing we're going to do is we're going to look it up on the table, and then I'm going to show you how to get the p-value on your calculator. So remember, we had degrees of freedom 3. So if you look in on your yellow table, and remember we're on table C, which is the side that has the skewed distribution, and we look in that row, our test statistic is 8 point something, and that falls between 7.81 and 9.35 on your table. So follow those values up to the column at the top, and that gives us a p-value of between 0.025 and 0.05. So the probability that our chi-squared test statistic is greater than 8.28 is somewhere between 0.025 and 0.05. So that's a pretty small probability. Now I'd like to show you on the calculator how to get that. So we'll fill in the conclusion, except we're going to leave that first blank where we fill in the p-value. We'll leave that part empty for now because we'll fill in the calculator value in just a minute. So because our p-value is less than 0.05, we will reject the null hypothesis. Now, our null hypothesis was that the proportion of tickets issued matches the racial breakdown of the city. So if we reject that, that means that there is good evidence that the racial distribution of traffic tickets issued is different from the racial distribution of the city's population. And that tells us that probably what's happening is one group is being issued more tickets than they probably should, maybe evidence of racial profiling going on in the police department. All right, now in your notes, there is a box that kind of indicates to you how to run the steps of the chi-squared test using your calculator. Notice the first 3 steps we kind of went over in class the other day. We put the observed counts into list 1, we put the expected counts into list 2, we entered the formula into list 3, and then we added up all of the components that are in list 3 so we could get the chi-squared value. Now, to get the p-value, what you're going to do is look at step 5 here, and notice what you're going to do is you're going to type in your calculator. Let's see if I can get the pen here. There we go. You're going to look for this function on your calculator. And to access that, you're going to hit second vars, and that's going to give you a menu of different distributions to use. And then it's going to ask for some parameters, sort of like when we did binomial probabilities. So what the calculator is looking for is chi-squared, which is your test statistic. You need some upper boundary, and then you need your degrees of freedom. So let me show you what that would look like on your calculator. So you hit second vars, and again, your vars key on your calculator is right here. And when you do that, it brings up a list of distributions. And so we've got like the first couple are normal, whatever. These, notice like 6 and 7 here, those are your chi-squared distributions. And we're looking for the CDF one because what we want to find, remember the chi-squared distribution kind of looks like this. And so we have our test statistic, which is here. And we want the area that goes to the right of that. So from the chi-squared statistic up to some really big number, which we have to put in sort of like an arbitrary upper bound. And we're going to find the area in between those two regions. So for this one, what I would type in is I choose chi-squared CDF. I type in 8.828 because that's my test statistic, and I'm going to go up to 1,000. And you could really put in any big number there. You could do 1,000, 5,000, 10,000, just something that's really big and for sure to be way, way off in the tail of that distribution. And then I put in 3 for my degrees of freedom. And when I hit enter, I get 0.0317 if we round that to 4 places. So that's my p-value. Now, if we go back to your notes, remember we said the p-value had to be somewhere between 0.025 and 0.05. And so the calculator gave us 0.0317, which is definitely in that range. So when you make your conclusion, you can either use that p-value that you get from the calculator, or you can use the table value, whichever one you prefer. Either way, you get the same conclusion, which is to reject the null hypothesis. All right, your assignment over the weekend is to try the 11.1 worksheet in the packet that you received the other day. And we will continue with Chapter 11 when I see you guys on Tuesday. Have a great weekend.